Let's continue our exploration in the wonderful world of slab waveguide modes, and let's again look at the diagram that we've been studying for the past couple of videos. So diagrams like these, Venn diagrams, where you have a set of discrete solutions over here, which turned out to be the guided modes, and which we talked about in the previous video. And then you have a set of continuous solutions over there, which we will talk about in this video. And again, we assume that you have some sort of previous exposure to waveguide theory, so this will just be a small refresher or a slightly different take on things. Now, if you look at a certain point in this part of the diagram where you have a continuous set of solutions, and if you plot the field profiles, then you will end up with something that you will recognize as a radiation mode of the waveguide, so with a standing wave pattern in the cladding. Now, if you look at a standing wave, you will know that this corresponds to two plane waves propagating in opposite directions. So the question you could ask yourself is why, in case of a slab waveguide with a core and a cladding like this, do you have these counter-propagating plane waves in the cladding? And will this be able to tell us something about why these modes actually form a continuous set as opposed to a discrete set? So see if you can identify a strategy to tackle this problem. So one way of explaining what's going on is perhaps a bit counterintuitive, and that is to start from our waveguides, core and cladding. And rather than considering this waveguide as it actually is, namely sitting in an infinite cladding material, we're going to enclose our waveguides in between two perfectly conducting metal plates, which basically have 100% reflection. Of course, that's a very different situation from the one that we're really interested in with an infinite cladding. But what we're going to do is we're going to look at this distance d between these plates, and then we're going to take that distance towards infinity. And then we will recover something that looks like our infinite cladding situation. Now, if you start from this diagram over here, it's very clear that if you have some sort of light that actually propagates in the cladding, so this means we're not talking about the guided modes where there is a small leakage of evanescent light that doesn't propagate, but if you do have a propagating wave in the cladding, then at some point this will encounter this reflecting boundary, and there you have your counter-propagating plane waves that will set up a standing wave for your radiation mode. Now, the thing is, will this help us explain why we have a continuous set of radiation modes? Because if we look at this particular situation here with a finite distance between these plates, we again have something similar to what we had in the previous video for guided modes. We have something that propagates up and down in a cavity inside the resonator, and we need to have a resonance condition fulfilled, namely a round-trip phase equal to 2 pi. In this particular case, something that looks like the radiation modes that we're interested in will still have a discrete spectrum because you have a resonance condition. Now, think a little bit about what happens to the spacing between these discrete resonances if you take the limit of the distance between these plates going towards infinity. And just to make your life a little bit easier, let's look at a situation where you can neglect what's happening here in the core. So let's just look at empty space in between two metal plates. And let's also not worry about any phases that you might accumulate on reflection. So let's just focus on the essential part, which is the phase that you accumulate when you travel up and down between these plates. So pause the video and think about what would happen to the distance in k-space between the different solutions as you increase the value of d towards infinity. Okay, so if we have our lights propagating up and down here, we again have the resonance condition that you should have a phase of 2 pi after a single round trip. So that will be something expressed by the following equation. So you have 2 times d, the total distance over which you propagate, and then times the propagation constant in the transverse direction. Let's call this one kx. So this is the total phase that you accumulate after propagating over the distance 2d. That should be equal to an integer multiple of 2 pi in order to have a resonance, in order to have a mode which can propagate while keeping its shape. Now what happens if d increases? Now the values on the right hand side, they're fixed basically, so they're all just integer multiples of 2 pi. As you clearly see here, if d becomes bigger, that means that the set of k values that you're interested in, they will become smaller and smaller, and they will move closer and closer together. So if you just plot this in a different way, in a different diagram, where you plot here, for example, the real part of the effective index of the mode, and there you plot the imaginary parts, you obviously have a set of guided modes, which are in between the refractive index of the core and the cladding. But then you have a number of radiation modes, which in our case, embedded between two perfectly conducting metal plates, are still discrete. But as you keep on increasing the distance between these plates, and then all of these guys over here, they will move closer and closer together. So you will end up with something that more looks like this. And in the limits of bringing d all the way towards infinity, then these will actually merge into a full continuum. This is a way of explaining why for your radiation modes, you do actually have a continuous set of solutions rather than a discrete set of solutions, simply by considering the limiting case of these two parallel plates and taking the distance between these plates going towards infinity.